This lesson deals with Supplemental Problem 2.1. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems starting on page 1. In A, we have a circuit with two power supplies, a plus 10 and a minus 10, two resistors, and two ideal diodes. And you find the current I and the voltage V. In problem B, we have the same circuit, but the resistor values are exchanged. Let's do problem A first. As I mentioned in the lecture notes, let's assume that the problems in this course are practical. And in a practical circuit, current comes out of the most positive power supply and goes into the most negative power supply. In other words, current will be coming out this way and going back this way. Let's take these diodes and represent them as resistors. I'll call this RD1 and RD2. And let's label the current from anode to cathode. If current wants to flow this way, it'll look like a short. If current wants to flow this way, it'll look like an open. If current were to go around this way, it would appear that ID1 is positive. And if current went around this way, it would appear that I sub D2 is positive. So I'm going to guess that diode 1 and diode 2 are both short circuits. I label the steps that I did here. You could start this problem a variety of different ways, but maybe the simplest one is the voltage V. I just have a short back to ground, so V is equal to 0. The short over here and 10 volts here, I have 10 volts across this 5K resistor. 10 volts divided by 5K is 2 milliamps. 2 milliamps entering this node, and the current that's leaving this node going in this direction would be this node voltage minus this node voltage divided by 10K. Well, this node voltage is 0, and this node voltage is minus 10. 10 divided by 10K are 1 milliamp. 2 milliamps entering, I have 1 leaving. If I want to find the current leaving this node, I could do it this way. The current that enters equals the current that leaves. 2 milliamps is entering, and a minus 1 milliamps entering. What's leaving is 1 milliamp. Since the current in ID2 is positive, greater than or equal to 0, and the current in ID1 is also greater than or equal to 0, then our guesses were correct. Let's take a look at problem B. In problem B, we have the same problem as A, except that the resistor values are exchanged. Now I have a 10K resistor here and a 5K resistor here. Take the same guesses again. And again, the voltage here is just going to be 0 volts, so that would be our first step. The current in this resistor now, though, is a little different. It's the voltage across it, which is 10 volts minus 0, divided by 10K, that's now 1 milliamp. And the current in this resistor is going to be this node voltage, which is 0, minus this node voltage, which is minus 10. Get 10 volts over 5K are 2 milliamps. The current entering is 1 milliamp. The current entering this way is minus 2 milliamps, and so that's what's leaving a minus 1 milliamp. But current can only flow in this direction. It can't flow this way, so it's a contradiction. Same problem, just different resistor values, and I get a different result. Let's randomly guess that maybe this is an open circuit instead of a short. Try it again. Now with a short circuit here, again, I've got 10 volts across this resistor. 10 minus 0, divided by 10K, that's 1 milliamp, and that 1 milliamp flows right into here. That checks. That's greater than or equal to 0. I've got to find the voltage across diode 2 and show that it's less than or equal to 0. This node voltage is 0, and this node voltage is going to be equal to this drop plus this drop. But since there's an open circuit here, there's 0 current times 5K, so that's 0 volts. The voltage of this node is going to be 0 minus 10. First node minus the second node gives me a plus 10. But for the diode to be off, the voltage across it needs to be less than or equal to 0, and it's not, so it's a contradiction. With current flowing, well, there's only one possibility left. Let's try that one. That's going to be that this is an open and this is a short. With an open circuit here, the current is equal to 0. I can now find the current flowing through here as the voltage across here minus here divided into 15K. And that's 1.33 milliamps. And that's also the current that's going to go through ID2, and that's going to check because it's greater than or equal to 0. So lastly, we have to find the voltage across the diode to show that it's less than or equal to 0. Let's find the voltage across this resistor, and that's going to be equal to the current times 10K. 1.33 milliamps times 10K. The rise in voltage here is equal to drops around the loop, so it's going to be equal to minus that drop plus 10. And that turned out to be minus 3.3 volts. The voltage across the diode is less than or equal to 0. Then it is an open circuit, and for this diode it was greater than or equal to 0, so it's a short circuit. I did a lot of guessing on this one, but it's still consistent with this idea being a practical problem in that the current is coming out of the positive power supply, most positive, and going into the most negative power supply. Just that this is another option in this particular problem where current didn't go this way, but all of it went this way. That was because of the resistor values. And this is Supplemental Problem 2.1.